Dear students, so in this particular module, we will learn details about factors that slower or enhance the rate of outer sphere reactions. The reactants reorganization occurs that allows the electron transfers to occur by adjusting the metal-ligand bond lengths. The FlynnCondon principle must be satisfied during the course of electron transfer. The solvent atmosphere plays a significant role on the rate of outer sphere electron transfer kind of reactions. As less interaction occurs with the solvent, the rate for the electron transfer processes are increased. The Eg or T2G orbital symmetry and electronic configuration influences the electron transfer rate. So let us discuss about the factors that affect the outer sphere electron transfer reactions. As I have discussed in the previous module that the delta G parameter can affect the rate of outer sphere redox reactions. So the delta G0 can be understood by the scheme that suppose this is one metal hexa-aqua complex. It is another M hexa-aqua complex. So what is the difference? One metal is in +2 oxidation state and another metal is in +3 oxidation state. So what happens? The solvent molecules are all around the one metal complex and the same with the second metal. So one metal complex is going to close enough with the another metal complex. There is a solvent barrier. The solvents are there in between. So for the better contact of the one oxidant to the another reactant needs the proper solvent reorganization, and therefore one complex, another complex. So what happens? Solvents are there all around and there is no solvent between when contact point of the both complexes, and that is the best way of the solvent reorganization for an electron transfer process to occur. The stronger interaction of the solvent molecules with the metal complexes diminishes the rate of electron transfer reaction. So the next is FlynnCondon factor, that is delta Gi. Change in the oxidation state of the metal center leads to the change in the ionic radius of the metal ion. That results in the alteration of metal-ligand bond length. Prior to the electron transfer to take place, the metal-ligand bond lengths must be adjusted in the complexes. However, according to the FlynnCondon principle, the nuclei are quite massive enough relative to that of the electrons. Therefore, an electronic transition to take place requires much less time than that of the nuclear motion. We must know that the electronic transfers to occur requires the time scale of 10 to the power minus 15 second, while a nuclear motion takes the time scale of 10 to the power minus 13 second. So FlynnCondon limitation must be fulfilled during the time of electron transfer process. Subsequently, angular momentum cannot be transferred during electron transfer process, while transition state is formed, as well as there is also a constraint of changing the electron spin. So what happens? Giving the example of two metal complexes based on iron. So iron hexa-aqua complex, where iron is in +2 oxidation state, another iron complex where iron hexa-aqua complex is there and the iron is in +3 oxidation state. So I have chosen the example of hexa-aqua iron complexes, where on one hand the iron hexa complex where iron is in +2 oxidation state and another iron hexa-aqua complex where iron is in +3 oxidation state. So upon interaction of +2 iron center complex and +3 iron center complex, they form a transient species where the bond lengths for both iron 2 complex and iron 3 complex are identical in terms of the bond distances, and this is the suitable position where the electron transfer process can occur, and when the electron transfer process is over, the iron 2 complex has been changed to the corresponding iron 3 complex and vice versa. So, the distance between the iron 3 and the oxygen of ligand water molecule is 2.05 angstrom, while in case of iron 2 oxygen distance is 2.21 angstrom. So, this is the bond length changes for the rigid iron 3 iron 2 complexes, but in the transient species the bond lengths have become equal, and therefore it facilitates the electron transfer process. In terms of electronics, the compression of FeO bond length takes place where it is D6 configuration, while elongation of FeO bond takes place when iron is in D5 configuration. So, what happens in the transient species? The electron transfer takes place from the T2G set where D4 configuration is there for the iron 2, and the iron F3 plus where just 3 D3 electrons are there in the T2G set. So, the electron transfer takes place from the T2G of the Fe2 center to the T2G of the Fe3 center, and that is the way this bond adjustment takes place, and later on the D5 becomes D6 and the D6 become D5. So, the D6 center is oxidized and it becomes D5, and the D5 center is reduced to become D6. Although it is not only the condition, but all the orbitals must be equal in energy for an electron transfer to take place. What does it mean? If orbital symmetry and their energetics will not be favorable, the electron transfers will not be favorable. So, let us talk about the potential energy diagram for such a outer sphere kind of reactions. So, the coordinates are taken are reaction coordinate versus G. So, if you see the potential energy diagram of such an electron transfer process, what happens? The R denotes the potential energy surface of reactants plus environment, while P denotes the potential energy surface of the products plus environments. So, there is a role of both potential energy of surface of the reactant plus environment and potential energy surface of the products plus environment. The potential energy surface of the reactant and the potential energy surface of the product, the reaction coordinate is shifted from the left to right, where potential energy surface of the product is there at the right end. So, the equilibrium is shifted, it is denoted by an arrow. The minima of the potential energy is shifted towards the right end. So, if electron transfer takes place, conservation of energy rule violated by following manner. If you see reactant, then product, and then product plus heat. How does it happen? The reactants combine together and they undergo electron transfer process and they form product. So, the electron transfer process has occurred, and now products are, if you imagine, are in unstable state. So, what will happen? If the products are in unstable state, they will try to relax, and when the product relaxes, it forms product that is in the ground state, and heat is liberated, the extra energy is liberated in form of the heat. Therefore, it is clear that it is photon that provides the required energy. The next important point is the symmetry of particular orbitals. So, if the transition is taking place from the orbital symmetry Eg to Eg, Eg is a sigma type of orbital, and that is dx2 y2 and dz2. So, one complex, suppose it is iron complex, iron 2 plus complex, and its Eg set is transferring the electron to the Eg set of another iron complex where iron is in +3 oxidation state. If such a transition occurs in an octahedral system, the Eg set is basically sigma star type. So, the change in metal-ligand bond length is large. Remember, if the transfer is from Eg set to Eg set, the change in metal to ligand bond length is large enough. Therefore, the rate for the electron transfer reaction is slow. If the complex has to work out to adjust its bond length in a greater manner, it will affect the rate of reaction and the rate of reaction will be slower down. So, what is the geometry of sigma type of orbital? It is axially oriented x2 y2 orbital and axially oriented dz2 orbital. So, when axial to axial transformation is taking place, electron is going to the axial type of orbital of the another species. These kind of reactions are reportedly slow. In addition, due to the ligand steric hindrance, the overlap in ML bond is also poor. Yes, if the ligands are sterically crowded, so what happens? They hinder for the metal complex to overlap with the another metal complex. As I told you that without overlapping of one complex to the another complex, the electron transfer is hard to occur. So, ligands steric hindrance also plays an important role, as feasible ligands will be attached to the metal center, so that the maximum overlapping can be resulted between both the reactants. The electron transfer process will be facilitated and will be rapid enough. On the other hand, if we talk about the pi type of symmetry, the pi type of d orbitals are dxz, dyz and dxy type of orbital, and these are referred as non-axial orbitals. So, what happens when the electron transfer takes place from one pi type of orbital to another pi type of orbital, that is in a better way referred as T2g orbital of the oxidant to the T2g orbital of the reductant, then the better overlapping of the ML bond is resulted. So, what happens? The better overlapping leads to the better adjustment of the bond lengths, and such an orbital symmetry prefers, and the rate of such electron transfer processes are greater. So, these orbitals T2g orbitals are pi or pi star type in nature. Besides, general observation noted for the first, that is 3D row metal, the second and third row metals also undergo faster electron transfer type of reactions because of the better overlapping factor occurs for the 4D and 5D orbitals. Means, if you are taking ruthenium instead of iron, the electron transfer rate will be better, and if you go for osmium, the electron transfer processes will be much more favorable than that of the 3D metals. In supplementary, the distortion of bond lengths is generally smaller in 4D and 5D metal complexes, because the strong fields with the extended pi conjugation such as 2,2-bipyridine, 1,10-phenanthroline type of ligands, etc. Introduction of these kind of chelating and pi chromophoric pi conjugation type of ligands in 4D and 5D kind of metals enhance the electron transfer rate. Another important factor is electronic configuration. The electronic configuration plays a vital role in the electron transfer process, because some configuration do not allow an electron transfers to occur, and therefore a electronic reconfiguration takes place and it requires additional amount of energy. Note, the reorganization of the system is consistent with the bond elongation and bond compression. That is called, in other word, the bond adjustment. One system needs to elongate the bond and other system needs to compress the bond, and by that way both the oxidant and reductant counterparts are now reacting in a homogeneous manner, so that the bond lengths for both the species are equal in nature. So, another example I have chosen is cobalt hexaamine complex, and in this case cobalt is in +2 oxidation state. Another cobalt hexaamine complex where cobalt is in +3 oxidation state. Now, these two complexes are interacting together and forming cobalt hexaamine 3+. See, one of the cobalt complex is isotopically labeled, so that you can understand that this cobalt, isotopic cobalt, has gone from +2 to +3 oxidation state, and the one cobalt complex that was in +3 oxidation state has now reduced to +2 oxidation state. So, if you talk about the electronic configuration, see what happens. The T2G set, the low lying orbital is basically T2G5 and Eg2 for D7 cobalt complex. Cobalt 2 plus complex is D7, and for this electronic configuration will be what? T2G5 Eg2. And for cobalt 3, what will happen? It is T2G5 and Eg1. Now, there is a possibility of electron transfer from the Eg of the cobalt 2 to the Eg set of the cobalt 3. So, what happens? This kind of electron transfer can take place. So, what will happen? As a result, the cobalt 2 plus has become cobalt 3 plus, and the cobalt 3 plus has become cobalt 2 plus. So, the electronic configuration, the D7 becomes D6 and the D6 become D7. But if you talk about the cobalt 3 system, that is D6 in configuration, so its T2G set is completely filled. When the T2G set is completely filled, the cobalt 2 plus, that is D7 in configuration, the electron transfer cannot take place from the Eg set to Eg set like that. It is also becoming what? Upon electron transfer, it becomes D6. So, its T2G set is completely filled, and now it is transferring the electron to the Eg set of the cobalt to become T2G5 Eg2. But for your kind information, I would like to tell you that once one of the D6 system, that is T2G D6 system, is quite stable, and it will never ever prefer to go for T2G5 and Eg2 configuration. So, this kind of configuration is unsuitable for electron transfer process. So, the system needs to be suitable by electronic configuration, so that electron transfer process can take place. So, T2G5 Eg2 or T2G5 Eg1, the electron transfer process is allowed and can be possible, but for T2G6 and T2G5 Eg2, this kind of electron transfer process is inhibited by electronic configuration. So, now it is clear that the electronic configuration plays a significant role in electron transfer processes. So, let us talk about summary. The summary says the diverse factors that influence the rate of outer sphere redox reactions have been discussed, like solvent reorganization, FlynnCondon principle, change in energy, electronic configuration, orbital symmetry, etc. The electron transfer occurs if all the orbitals of both the redox couples are of the same energy. Means in the transition state, the bond lengths are adjusted, and when all the bonds become equal, the electron transfer takes place, resulting to the formation of electron transferred oxidant and reductant. The interaction with the solvent molecules plays significant role, since as much interaction will occur, the rate of electron transfer will decreased. Means there should be least interaction of the complexes with the solvents. As much solvents will be bound as interacted with the complexes, the rate of reaction for the electron transfer process will be quite slower. Further, the metal-ligand bond distances change to allow the electron transfer process. As I mentioned that homogeneous or unique bond distances are the suitable condition for the electron transfer process to occur. Next, the electron transfer process will be allowed if the ligands are less sterically crowded, means like ammonia, water and chloride. Such systems are favorable for the electron transfer process, but the heavy sterically crowded systems, ligands attached to the metal center, will inhibit the rate of reaction, and most usually they slower down the rate of reaction, and eventually both the reactants must come closer for the tunneling process. Tunneling process means an electron is transferred from the one species to the another species, the oxidant to the reductant, and that is directly not jumped but requires a tunnel. So tunnel is what? The better overlapping of the oxidant and reductant, so that the electron follows that overlapped tunnel by orbitals T2g to T2g or Eg to Eg, and it certainly from the oxidant to the reductant, and that way the electron transfer process occurs via outer sphere mechanism, and eventually the coordination sphere of the both the complexes retain intact.